We're going to throw over to Stephen Suter. He's an electrical engineer with 40 years experience and specializes in the design, construction, and management of automated and remotely controlled energy, wastewater, and irrigation systems. After being an engineer at Australian Paper, Stephen founded Latrobe Valley Engineering Services, a company specializing in the process control and automation of water and wastewater treatment plants across Eastern Australia. With the just desperate need for advanced innovation in the growing energy marketplace, Stephen founded Alternate Energy Innovations and applied this extensive automation knowledge to the energy sector, using his forward-thinking approach to develop smart energy solutions for now and into the future.
Okay, so so I'm Stephen Suter. I'm the engineering manager at Alternate Energy Innovations. I'm a process automation engineer, and as Kelly said, I started at Australian Paper, which is about 5 minutes away, about 40 years ago, and developed the other two companies that he mentioned. AEI is an engineering-based company. It's located in Moore, right near all the power stations, so it's probably appropriate that we get involved in energy systems. And our aim at AEI is to allow you, that is the operator, to control your time, your cost, and your future. So what I want to talk today about is implementing new technologies on the farm. Renewable energy, it needs to be more than just supply, install and forget. And like many systems in the past, that's been the case. I want to talk to you about an engineering approach that we've done at Willandra Farms. I want to talk about on-farm microgrids and how they work and can be valuable in the future. And I want to talk about the future of power, which is working with the power network and being involved in flexible demand, which is a mixture of the current demand management, load shifting and live pricing. So where have we been? This is really just to indicate that VS drives were something that we've probably used for 20 years or nearly 30 years, probably a bit less in farming, but it's really important that we use them correctly. Now, the aim of the VS drive supplier in the last 20 years is to sell you a VS drive, and really the aim should be to use it properly. So whilst they can solve all problems that people think, they can solve a lot of them, but you have to get it in the right circumstances with the right control strategy. And I really question how many VS drives have been installed on farms that are providing the expected benefit. And I think that's probably fairly low, because you really need to know how to use them properly. So where are we now? We're on a similar path with solar. The sell is, let's put it everywhere. It'll cut your power cost. In my view, in reality, it's suitable in some cases. That's ideally suited in some cases, but not all. But when optimised, can significantly cut power costs, and the optimisation is the critical bit. And how many solar systems have been installed that are not meeting the expected benefits that you had in mind when you install it? And we'll go through some of the reasons why that might not be happening. And where are we heading? Probably more importantly, we're about, according to the battery people, to put a lot of batteries in everywhere, and there's no doubt this will happen. But again, the critical thing is that everyone says put them on all your solar systems, further cut your power costs. But my view's simple. Before thinking about a battery system, optimise the efficiency of your process first, optimise the usage of your alternate energy, and then think about putting a battery in. And in the future, will we be saying we've put a lot of batteries in but haven't created the benefit? So the common link in all these is the sell. The aim of the person selling it is to sell you equipment and not a solution. So each individual piece of equipment works well in the ideal environment, but all can work very well in an engineered, automated and optimised system. And the key word here is system. And I believe the system is the bit that enhances the chance of you achieving the expected benefit. Just want to go back to a diesel generator to show the difference between where we were and where we're heading. The diesel generator is a scheduled, controlled generation source that you can go and stop and start, and it will run at the generation level of the devices and the loads you connect to it. And you can meet any of the patterns shown to the side. Renewable energy is the exact opposite. It is completely unscheduled generation. On one day, it can be perfect. On the next day, it can be not too bad. On the next day, it can be very ordinary. And on the next day, it can be terrible. And in fact, you control nothing about it. You just get what you get. So when you put solar with fixed power loads, so a fixed power load is an example of that is pumping to a pivot. So the load doesn't have to be perfectly constant. It just means that you don't have control over what the load is and it remains fairly steady. So the percentage of load power supplied by the solar is very, very important. Too low a load can be very costly. So if you look at the graph in the top left here, that's almost the ideal situation. Down these sides here, you could be starting to get into trouble if you're moving load from off-peak to these areas here. Because as you have less solar generation creating the power you're using, the higher the cost is, especially during the weekdays when you're on peak. So when the profile of the solar gets worse, you're spending more time where you're creating a lower percentage of your load from the solar. And obviously on the really bad day, you're almost saving nothing from the solar, but you're using on-peak power. So in the case of the last one on the bottom right here, you'd be far better off operating at night. Obviously, if you've operated at night and then you're in the daytime, then you're always going to be better off by using it because that will still be the cheapest. So just a quick graph, and I won't go into it too much detail. Basically, the blue bar is the percentage of the load power that's supplied from the solar. So as you move to the right, the percentage of load supplied from the solar is less. The orange figure, the orange line coming up here, is the cost of operating on peak. So obviously, as you supply less of the load from solar, the cost increases, and it gets to the stage about halfway or around there where you might as well operate at night and get the feed-in tariff during the day. So this graph is fairly dependent on the ratio of on-peak to off-peak network tariffs. And for those that live in Gippsland where we live, we've probably got one of the worst ratios of on-peak versus off-peak, which is about 4 to 1. It's typically 2.5 to 3. So the critical thing is just make sure that you're not operating fixed load systems on solar during the day when you have low levels of solar generation rather than operate at night. So just move back to operating at night and get your feed-in tariff during the day. So the impact of solar sizing is actually fairly critical. If you undersize solar, then you decrease the percentage of load power supplied from the solar and you increase the chance of reducing your profit. So you can see there, because we've raised the power usage from before to above the solar generation, then you're going to make less money out of that if you want to operate it during the day compared to at night. So the same goes if you oversize solar systems, that can result in a higher cost of installation and excessive power to the network, and therefore that may not be of benefit. And I think people need to understand in the future that feed-in tariffs are probably heading close to zero rather than where they are now. They've been dropping for a significant amount of time, and I think in some states they might already be zero. And the other thing that is significant, I believe, is on dairies. A lot of people don't believe they get the benefit of solar on dairies. And I think one of the key reasons is that people size the solar on the dairy to suit the profile that exists today. And often it's limited. The solar provider may tell you that you should limit to 29 kilowatts, and usually that's to make his life simpler, not necessarily give you the best answer. There's often a limited roof space. And then when you shift load, later from off-peak to on-peak using a time clock, which is what is often done with water heaters, then you further decrease the percentage of load power supplied from the solar. So when you increase this bit in the middle here, you move further away and have a lower percentage of power generated from solar, and therefore you further decrease the profit you make. So what I want to talk about now is an engineered approach to a system we've installed at Willandra Farms, which is owned by Wilco and Sandra. It's a 150 hectare organic dairy farm, and it's located in Clydebank in Eastern Victoria, which is near Sale. This is the existing farm assets, and we'll just go through this relatively quickly because I want to look at a particular part of it. But all of the system was fully manual when we first got there. It has 4 main connections to the power grid, which we call NIMIs. And it has a mixture of, and it basically has fixed power operations. So fixed power operations mean that the pumps operate basically at a constant power rate, and that may even be the case if they have a variable speed drive. So in this case, and this is only part of the system, the river pump can pump to the pivots or to the dam. The bore pump can pump to the pivots or the dam, and there's also a diesel pump that pumps from the dam to the pivots. And basically that's all fixed power, all manual. So in this project, one of the key things we've done is provide a mixture of power applications. And that is we changed some of the fixed power applications to variable power applications. So now the river pump only pumps to the dam, the bore pump only pumps to the dam, and 2 new floating pumps were installed on the dam that now pump to the pivots. They are all fitted with variable speed drives. So interestingly, even the ones that are fixed power, which is the one that pumps to the pivot, they're fitted with variable speed drives, but they're fitted with variable speed drives so that we can operate at a constant pressure at the pivot and therefore optimise the energy used. But when it's running, the energy will pretty much be fixed. What the variable pumping systems allow us to do is vary from about, in this case, from say 10 to 45 or 10 to 37 kilowatts, and that means we can operate them at any power rate that we want to. And because we now pump to the dam rather than direct to the pivot, we can run them at any time, even when we're not irrigating. Now, just one of the things of interest, if you are running a system at the moment, you may actually find that adding or enlarging a dam may give you a better result than installing a battery, but that's probably another discussion for another time. And this is the AEI SmartBox app. The AEI SmartBox is our product that controls all of this, and it allows you to control different applications, set schedules for today, tomorrow, and overmorrow, and it allows you to look at trending and alarming. So this is the end result of the solar and automation at Willandra in the main power plant area. So this graph shows the operation of 150 kilowatts of solar, which is the green. The lined area in the middle is the power used, and the orange is the feed from the grid. So it's from the grid when it's above the line and to the grid when it's below. And the system has 56 kilowatt hours of usable battery, and I'll explain what that's for shortly because it's not for what you would normally use it for. The process is now fully automated, and for this test, the batteries were actually off. And the reason for that was we wanted to see how it performed without the batteries providing the role that they did. So the key thing to notice from this is the usage of solar is extremely high. So in fact, the usage of solar is 90%. So 90% of the solar was used and 10% was put back into the grid. And pretty much the reason it was put back into the grid was that we were generating more power than we could use. On this particular day, which is the perfect solar day, the load was powered by 94% solar and 6% grid. Now, those numbers are very high for any solar system. And the reason we're able to do that is we have variable and fixed load. So from an efficiency point of view, this is a very, very high efficiency in the use of renewable energy. So by creating flexible demand, that is variable and fixed power applications, we can pretty much make the load follow any renewable power generation that exists in a day. Now, just to explain what the battery's used for, what the battery's used for is to smooth the generation out so that the control can work better. So all the high and low peaks that come through the solar generation, they can be smoothed out and allow for less switching between which applications are running. So you don't want to be turning a pivot on and off too much, but it's not too bad to let the variable power demand applications run for significant times. So again, a very high use of alternate energy in all cases. So what we did next on the Willandra farm is we looked at using a microgrid. And the reason we used the microgrid is because we couldn't use the top end of the solar that was left. So we had excess solar, and how could we use that? Now remember, the excess solar might be higher when there's not a need to do some of the irrigation processes, and therefore we may end up with 50% of solar used. But obviously, if it's not connected to this particular transformer where the solar is being created, then we don't have a use for it. All we can really do is put it back into the grid and contribute to the problem that we all know about, which is too much renewable in the system that may not be being used. So this is a complicated graphic, but I'll simplify it for you. In the middle here is the power generation system, and that's where the power is being used today. And what we have the ability to do with the control microgrid is, if we have a spare 10 kilowatts of power at the transformer, the main transformer in the middle here, we have the ability to move exactly that amount of power to the NIMI up the road, or in this case on the other part of the farm, and we can use 10 kilowatts into the river pump at exactly the same time. And the reason we can use 10 is the river pump is a variable power application. So it can run from about 10 to 45 kilowatts. So when we have 20 kilowatts of excess solar at the transformer, we can then change that to 20 kilowatts being used to pump to the dam. So what we can end up doing is getting close to 100% usage on the farm, and therefore because there's no excess alternate energy or renewable energy, there'll be no impact to the outside power network. So just looking at that and then looking now at the national grid, basically what is happening at the moment is that we're moving from customers to participants. So the national energy networking has changed and will continue to change. So we're moving from a large conventional power plant base, which is obviously scheduled, controlled and relatively stable, and it can pretty much match any load that the total customer base creates. And now we're moving to 100% renewable energy, which is largely unscheduled, uncontrolled, and can't always provide the response we need. And it doesn't matter how you look at it, the network needs help, and AEMO, the operator, will need many customers to become participants. So one way of becoming a participant is to be involved in live pricing. And the way live pricing makes you a participant is that when the market is low in price, that usually means there's an excess of renewable energy in the system, And if you move your irrigation to take use of that low price, then you are using more renewable energy and helping to move the network back into a controllable space. So in this case, this particular system is installed at McAlpine's Dairy Farm in Woodside in Eastern Victoria. It has a 90 kilowatt bore pump feeding 4 centre pivots, which were very old, and it supplies water to a dam on another part of the property. So it's got 4 fixed and 1 variable power application. You can set the scheduled hours as we discussed before, and now the whole system is fully automated and saves significant time for the farmer in operation. So this is just an example of a weekend where we have the orange line is the base price for power off peak. The grey line is the live price of power in Victoria on that weekend, and the blue is the kilowatt hours per 30 minutes of the pump system running. So what happened when the price was low during this period here, the pump system ran, and when you compare it to fixed off-peak pricing, the system ran at 39.5% less than fixed pricing. We did have a bit of a failure in the middle there that missed an opportunity. If that had been used, it would have been 52% less. And when you compare usage charge and demand charges, it runs at about 35 to 43. Now, the result will depend on where you're running, how often you're running, but basically, if you can operate equipment based on the live pricing market, when it's low, there's potential to save significant money. But moving forward, the answer is flexible demand. So demand management is becoming flexible demand. So demand change requests typically last for a couple of hours. So that's a period of time where the network is in a bad state and action needs to be taken. So conventional demand management is usually high demand in the network, and that's handled at the moment by texting people to reduce the load in the household, and then they'll receive a payment. And it even got to the stage one time in Victoria where Australian Paper, the paper mill next to us, which is the largest pulp and paper mill in Australia, was asked to shut for a day, and they were paid for a significant amount for shutting. So what flexible demand management means is that you still have the normal demand management, which is reduced load, and then in this case, we can shift the load back in time or into the future. And then there's also the possibility now that you'll be asked to increase load on a certain day because the level of renewable generation is higher than expected. And then there's the potential to shift that load forward. So if you were planning to irrigate tomorrow and the next day, you could be paid to bring that load forward and do it today. So where does that fit in with farming? I think farming and flexible demand can go hand in hand, and that the farming sector can play be a large participant in the flexible demand management area, especially with irrigation loads and water transfer loads. Clearly, we wouldn't want to drop off the dairy and say, sorry, you've got to shut your dairy because we've got to cut the demand down. But there's ways of getting around that and use that as part of the system with both generators and batteries. And these application loads can automatically be reduced. That's shift the load to later, or increased, shift the load to earlier, with little or no impact on the irrigation schedule. So in critical circumstances, shutting farm loads around the town may mean that the town power stays on. Quickly cover the capabilities of the Smart Box, which we've basically covered through the documents. It can irrigate, control irrigation, control power management, control a microgrid, and be involved in flexible demand management. And that's my contact details. Thanks very much for your time.